Okay, so the last topic on logs. For this one, we're going to be looking at the application of logs to exponential curves. And we can use logs to turn exponential curves into straight lines, which we can then analyze using the equation of a straight line, which you're familiar with. So we're going to turn exponential curves into a straight line. Now this is a curve you're familiar with, y equals x squared quadratic. Now using the y and x values, we can convert them, if we use a log scale, into a straight line. So y equals x squared, and the straight line is log of y equals 2 log x. And that's our straight line. So you can make some quick notes. Okay, if we look at the exponential equation y equals ax to the power of n, we take logs on both sides. That's going to give us log of y, which is equal to log a x to the power of n. Now we can simplify the right hand side using the addition rule. So log of y is equal to log of a plus log of x to the power of n. Now we can simplify further using the power rule. So we have log of y, which is equal to log of a plus n log x. I'm going to take this, because log x is our variable and log y is the other variable, I'm going to rewrite this as log of y, which is equal to n log x plus log of a. Now I've rewritten it because we know our straight line equation as y equals mx plus c. So our constant term in this case is log of a, our gradient is n, so those are our two constants, and then our x variable is log of x, and our y variable is log of y. If you want to pause that and make some notes. Okay, example. So we're looking at some cities in the UK, and we're ranking them based on the population in those cities. So we've got Birmingham, Leeds, Glasgow, Sheffield and Bradford, and they're ranking in the UK by the number of people that live in them. We can model this by the formula P is equal to A r to the power of n. A and n are both constants. We could draw a simple scatter graph. Looks like that, and you can see there's a slight curve there, exponential curve. Our task then is first to tabulate the values of log r and log p to 2 decimal places, and then we're going to plot the table log r against log p, and then draw a line of best fit through the points. So there's our table, log r and log p. What I want you to do is use your calculator and fill in the data. Log to the base of 10 of r across there, log to the base 10 of p across there. And what I want you to do is click pause now, fill those in, and you can check in just a minute. Okay. So Birmingham 0.3, Leeds 0.48, Glasgow 0.6, Sheffield 0.7, Bradford 0.78, and then with the population in Birmingham, log to the base 10 of 1 million, 6 zeros is 6, and then Leeds 5.86, Glasgow 620,000, Sheffield 530,000, and then Bradford. So I can plot them log P against log R, and then draw a line of best fit through those. Finally, we're going to use the graph to estimate the values of A and N to two significant figures. Okay, so we're going to try and rearrange P equals A to the power A R to the power of N in the form Y equals mx plus C. So we got P equals A R to the power of N. We want to write that as a straight line equation. So we take logs on both sides as we did earlier. So we can write log of P is equal to log AR to the power of N. And then we can simplify this part using the addition law. So log of P is equal to log of A plus log R to the power of N. We can simplify this further using the power law. So log P is equal to log A plus N log R. Then rearranging, log P is equal to N log R plus log A. Now, equation of a straight line is Y is equal to mx plus C. So log A is our intercept, y-intercept. And N is our gradient. So using our graph, we can determine the gradient and the intercept. So from our graph, you can see that log A intercepts the log P axis here, and that's going to be at 6.2. and we can determine A then as 10 to the power of 6.2. N is the gradient from the graph, and hopefully you've sketched it out. Use the rise divided by the run, and you should be getting minus 0.67. There's a second type of exponential curve where we have y is equal to a b to the power of x, and our variables are y and x, which is the power. So in a similar sort of fashion, we're going to take logs, and we can also express this in the form y equals mx plus c. So taking logs on both sides, we have log of y is equal to log a b to the power of x. Simplifying that using the addition law, log of y is equal to log of a plus log of b to the power of x. And then simplifying that using the power law, we've got log of y is equal to log of a plus x log b. So quick rearranging, log of y is equal to x log b plus log a, and then we've got our y equals mx plus c, and our intercept then is log a, and our gradient in this case is log b, because our variable is x in that case, and our variable here is log y. So we look at our second example. This graph is representative of a population of bacteria, the growth of the population of bacteria over a time t hours. They've given us the gradient of 0.6 and the intercept 0, 2. So scientists suggested that the growth can be modeled by P is equal to A, B to the power of T. A and B are both constants to be found. Write down the equation for a line. So part A, we're going to write down the equation for the line. We're going to be using our y equals mx plus c. So we've got P is equal to A, B to the power of T, taking logs on both sides. Log to the base 10 of P is equal to, we can use the addition law and the power law straight away. So we can say log A plus T log B. Now we know that the gradient is 0.6, and we know that the intercept is 2 and the gradient is 0.6, so we can write that's going to be equal to the gradient intercept is 2 plus 0.6t. If you want to rearrange it, you could say log P is equal to 0.6t plus 2. So as your y, as your x value, as your gradient 0.6, and 2 is your intercept. Part B, we've got to find the values of A and B. Now from part A, we know that log P is equal to 2 plus 0.6t. We can write this in powers of 10, so we could say P is equal to 10 to the power of 2 plus 0.6t, which is the same thing as 10 squared. Oops. Times 10 to the power of 0.6t. 10 squared is 100, and 10 to the power of 0.6 is, looking on your calculators, 3.98. to the power of t. So if we compare this with our original equation, P is equal to A, B to the power of t, we can see that A is equal to 100 and then B is equal to 3.98. And we move on finally to part C of the question, which asks to interpret the meaning of the constant A. So what does A mean? A equals 100. So we got P equals 100 times 3.98 t. When t equals 0, at time 0, at the start, P is equal to 100 times 3.98 to the power of 0. Anything to the power of 0 is 1, so P equals 100. So at the start, the population of bacteria is equal to 100. So some questions for you to attempt now. And finally some questions for you to try. 8 questions, off you go.